My name is Jim Olson, and this video is titled Counting Balls, Squares, and Triangles. I came across a lovely question on Twitter that I found to be very interesting, and I wanted to share it with you. It all started with a tweet on Twitter. This nice graphic was given. Number of spheres plus number of squares equals number of triangles. And I like counting problems like this, so I fiddled with it for about a half an hour and I couldn't get it to work. So I asked some questions and the replies came back clarifying that when you're counting the squares here, you need to count all the squares, not the individual unit squares. And when you're counting the triangles, you need to count all the triangles of all sizes. And I'm not sure if I'd ever really solved that problem, so I started working on this. I put together a web page with some of the GeoGebra links and Desmos links that I worked with, and so you can visit this. If you would like to do some of the activities ahead of me, find the links there. So I'm going to define three functions so we can keep track of the three counting problems. First of all, the tetrahedral numbers are the stacked up oranges or cannonballs here. We're going to use T of n for that. Sometimes T of n is used for the triangular numbers, but I wanted to just use a single letter, so I'm using T of n for the nth tetrahedral number. Secondly, we will use S of n for the number of squares of any size in a staircase of n steps built using unit squares. And finally, M of n is the number of triangles of any size in a triangular matchstick arrangement of side n. So imagine this right-hand figure made out of matchsticks. Probably a problem from many years ago. I am going to be doing two examples, the original example, which is here, and then one that is one notch larger. The first thing we need to look at is the tetrahedral numbers. A tetrahedron is a triangular pyramid. The Egyptian pyramids have a square base. These tetrahedrons have a triangular base, and they're made up of triangular numbers. So let's take a quick peek at some triangular number information. I have this web page here, and we have the first 6 triangular numbers here. T1 is 1, T2 is 1 plus 2, T3 is 1 plus 2 plus 3, which is 6. They are using a different notation here than I'm using for the tetrahedral numbers. So we add up triangles to make the tetrahedrons. Sometimes a tetrahedron can be thought of as made up of multi-link cubes like this, and that's a good way to experiment with triangular numbers. So let's take a look here. In the diagram, we have the first 4 tetrahedral numbers. The first one is just 1. It's kind of degenerate, but that's where we like to start counting. This one is 4 because it's 1 plus 3. This one is 10, 1 plus 3 plus 6, and so on. There is a nice formula to calculate any tetrahedral number directly, and it's T of n equals n times n plus 1 times n plus 2 over 6. Maybe let's do n equals 4. The 4th tetrahedral. So we would take 4 times 5 times 6 and then divide by 6. And that is in fact 20. But why is this formula what it is? At the Wolfram's demonstration project, they have a nice demonstration of this formula. So let's go ahead and look at the Wolfram Demonstrations Project. Here I am at the Wolfram Demonstrations Project. And what we have here are actually 6 copies of the tetrahedron. And I can change the number of blocks. even all the way down to the simple tetrahedron, or up to a tetrahedron here that has 5 cubes in the base. So this would be tetrahedral number 5, and we have 5 copies of it. And the cubes are arranged so that they can fit together here nicely, and notice what we get. This rectangular solid is 5 high. This dimension is 1 more than 5, which is 6. And this dimension is 2 more than 5, which is 7. So the total volume here is 5 times 6 times 7, and we would need to divide by 6. This is a visual way of seeing why the formula works. Okay, now we've looked already at the tetrahedral numbers. Now let's look at the way we're going to count stairs in the staircase, S of n. And we're going to use GeoGebra for this. So here are these staircase squares. And this is one larger than the example in the original problem. What is the number of squares in the staircase? Well, I could have the unit square here, and I see that we have 1, 2, 3, 4 along the bottom, and then 3, and then 2, and then 1. So we have 10, and that is a triangular number. But I could also have a square of size 2. So let's bump this up to a square of size 2 and see how many we have. I can put one here, but I can also shift it to the right. So I have another one there, and then I can come up here, and it looks like I have 1 there. So there are 3 squares of size 2. And then if I go to size 3 here, a 3 by 3 square, actually, there aren't going to be any of these. None of these are going to fit in here. Kind of interesting how that works. So we have 10 that are 1 by 1 and 3 that are 2 by 2. So we have 13 squares. So if we go back to our original question, the number of spheres here is 20. The number of squares here, we have 3 plus 2 plus 1. We have 6 individual unit squares. And there is 1 2 by 2 square here. So there's going to be 7 squares in our original problem. In the larger example that I did over on GeoGebra, we have 35 in the 5th tetrahedral number, and we had 13 in the 4th stair step. Now we need to investigate the matchstick problem, counting the triangles in this figure. And again, we're going to use GeoGebra. This is the matchstick triangles for you to experiment. What is the number of triangles in the big triangle? Okay, so the big key to investigating the matchstick problem is to think about it as 2 sub-problems. First of all, we're going to work with triangles pointing up. And we can vary the size, so we're going to work with these triangles that are pointing up. And then we're going to switch and work with triangles pointing down. So we break the problem up into 2 sub-problems, each of which is a little bit easier to solve. If you'd like to stop the video now and try to figure this out on your own, I welcome you to do that. So let's count the triangles that are 1 on a side. Along the bottom here, I have 1, 2, 3, 4, 5. That's nice because this has 5 on an edge. Up here, notice what we get. 4, then 3, then 2, then 1. 5 plus 4 plus 3 plus 2 plus 1 kind of a theme that we have going here. There's 15 triangles of that type. Now let's bump it up a notch and look at these that have side 2. How many can I have shifting across the bottom? As you might expect, there are 4. And when we come up a level, how many do we have here? Yes, indeed, there are 3. Here there are 2, and 1 more at the top. What about size 3? Coming across the bottom, I have 3 plus 2 plus 1. Nice pattern going here. Size 4, I have 2 across the bottom, so we have 2 plus 1. I have 3 of that type. And finally, the entire triangle. I can put this in here, and there's going to be 1 of that type. So there's quite a few triangles that are pointing up. Now I would like to look at the triangles that are pointing down. And I'm going to start at the bottom again. How many triangles are there pointing down? There were 5 pointing up, and there are 4 in between here pointing down. And our pattern is what we would expect. 4 plus 3 plus 2 plus 1. Now let's try for size 2. Notice that size 2, I only have 2 going across the bottom, and as expected, I have here. So there's only 3 of this type, 2 plus 1, which is 3. And then if I go to size 3, notice that it does not fit in here. So in this larger example, there are 35 triangles that are pointing up. There are 13 triangles pointing down. 35 and 13 is 48 triangles altogether. Now let's go back to our original problem and do the same thing. We're first of all going to count the triangles that are going up. Okay, I'll put the information right on the screen. Along the bottom, we have 4 triangles that are pointing up of size 1. And then we have 3 pointing up, and then 2 and 1. So we have 10 with a side length of 1. With a side length of 2, we have 3 across the bottom, then 2, then 1, which is 6. Side length 3, 2 plus 1 is 3. Side length 4, that's the entire triangle. There's 1 of those. So the number of triangles pointing up totals up to 20. Now if we count the triangles pointing down. Side length 1, we have 3 in here, and then 2 and 1. Side length of 2, I only have 1. It's fitting right in here. Interesting that the pattern for the triangles that are pointing down is slightly different than the pattern for the triangles pointing up. So the total is 7 pointing down. And so the number of matchstick triangles for the figure with 4 on a side is 27. But lo and behold, the 20 triangles that were pointing up, that was T4. And the triangles pointing down, that was S3. This is starting to come together. So here's what we have. 20 cannonballs here in the tetrahedron, 7 squares in the stair steps, and 27 triangles in the matchstick figure. And in our larger example, we had 35, 13, and 48. But what's the connection? In mathematics, we always want to know why. Okay, first of all, the number of triangles that are up pointing, the up pointing triangles in the matchsticks, the matchsticks figure of size n is equal to the number of balls in the tetrahedron, which has 4 along the edge of the base. And the number of down-pointing triangles in the matchstick figure is equal to the number of squares in the staircase of size n-1. Notice that this has only 3 on the edge where this has 4. But we can say more, looking down at the individual triangles themselves. The number of up-pointing triangles of size k in the matchsticks is equal to the number of balls in layer k in the tetrahedron. So consider this diagram that's a tetrahedron, and consider this matchstick figure. This is k equals 1. So over here, I want to take the balls in layer 1, which is 4 plus 3 plus 2 plus 1. There are 10 orange balls in the base. And over here, we also have 4 plus 3 plus 2 plus 1. It's a beautiful thing. Now let's take a look at the down-pointing triangles. The number of down-pointing triangles of size k in the matchsticks is equal to the number of squares of size k by k in the staircase. Again, let's look at k equals 1. K equals 1. Here are the down-pointing triangles, 3 plus 2 plus 1. And k equals 1. Here we have 3 plus 2 plus 1 squares. I will let you take a look at k equals 2 and so on in these two cases. So symbolically, here's our conclusion. T of n plus s of n minus 1 is equal to m of n. So I want to point out again that I have a web page where you can fiddle with this yourself, work with the GeoGebra. And I also have a Desmos file where I start looking at the formulas. And here is a formula for the number of squares in the staircase, and here is a formula for the number of matchstick triangles. And I look at 3 different ways you can look at those formulas. This slide deck was downloaded from Slides Carnival. I hope you have enjoyed this video. Counting problems are very interesting in mathematics because there's always underlying reasons. Triangular numbers, tetrahedral numbers are very lovely. I encourage you to investigate more. Have a great day.